Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, Properties of Infinite Series 1, is the first in a series of 3 videos on the properties of infinite series, and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the video Introduction to Infinite Series prior to watching this video. In this video, we will be discussing the test for divergence, the integral test, and p-series. As a test for divergence, the following theorem holds. If the infinite series from k equals 1 to infinity of a sub k converges, then the limit as n approaches infinity of a sub n equals 0. The test for divergence then follows. The infinite series from k equals 1 to infinity of a sub k diverges if the limit as n approaches infinity of a sub n is not equal to 0. It is important to note that the reverse of the theorem does not hold. If the limit as n approaches infinity of a sub n equals 0, then no information about the convergence or divergence of the series is obtained. As an example, use the test for divergence to determine if the following series diverges. The sum from k equals 1 to infinity of k over k plus 1. We take the limit as k approaches infinity of k over k plus 1. To solve the limit, we divide each term in the numerator and denominator by k. This gives us the limit as k approaches infinity of 1 over 1 plus 1 over k. This is equal to 1 over 1 plus 0, which simplifies to 1. Since the terms of the series do not approach 0, this series diverges. For the integral test, the following theorem applies. Let f be a function that is continuous, positive, and non-increasing on the interval from 1 to infinity. Let a sub k equal f of k for all positive integers k. Then if the proper integral from 1 to infinity of f of x dx converges, the series from k equals 1 to infinity of a sub k converges. And if the proper integral from 1 to infinity of f of x dx diverges, the series from k equals 1 to infinity of a sub k diverges. As an example, let's use the integral test to determine whether the following series converges or diverges. The sum from k equals 1 to infinity of k times e to the negative k squared. The function f of x is equal to x times e to the negative x squared is defined on the interval 1 to infinity and is continuous and positive. If we take the derivative of f, we get e to the negative x squared minus 2x squared e to the negative x squared, or simplified as e to the negative x squared times the quantity of 1 minus 2x squared. On the interval 1 to infinity, this will always be a negative, so the function is decreasing for all x greater than or equal to 1. Therefore, the integral from 1 to infinity of f of x dx is equal to the limit as b approaches infinity of the integral from 1 to b of x times e to the negative x squared dx. To solve this integral, we let u equal e to the negative x squared. This makes du equal to negative 2x times e to the negative x squared dx. When we substitute, we also substitute the limits of the integral so as to get the limit as b approaches infinity of the integral from e to the negative 1 to e to the negative b squared of negative 1/2 du. We can take the negative 1/2 out as a constant and take the integral, giving us negative 1/2 times the limit as b approaches infinity of u evaluated from e to the negative 1 to e to the negative b squared. This gives us negative 1/2 times the limit as b approaches infinity of e to the negative b squared minus e to the negative 1. When we take the limit, we get negative 1/2 times the quantity of 0 minus e to the negative 1, or 1 over 2e to the first power. Since the improper integral converges by the integral test, the series also converges. A P-series is an infinite series that takes the form, the sum, from k equals 1 to infinity, of 1 over k to the p, where p is a positive number. This sum will be 1 plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, and so on, including 1 over n to the p. This series is sometimes called the hyperharmonic series, since the harmonic series is a special case of the p-series where p equals 1. The following theorem applies to p-series. The sum from k equals 1 to infinity of 1 over k to the p converges if p is greater than 1, and diverges if p is greater than 0 and less than or equal to 1. It is often possible to approximate the sum of a convergent p-series by finding its upper and lower bounds. To calculate the bounds of this convergent series, we first consider the area under the graph of f of x is equal to 1 over x to the p on the interval from 1 to infinity, where p is an integer greater than 1. This can be computed as the integral from 1 to infinity of dx over x to the p. First, let's consider the sum of rectangles formed by the intersection of the graph with the integers for x. The area of the rectangles will be 1 plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, and so on, or the sum from k equals 1 to infinity of 1 over k to the p. This sum will be greater than the area under the graph of 1 over x to the p, or the integral from 1 to infinity of dx over x to the p. The next set of rectangles starts on the left side of the interval. In this one, the areas of the rectangles can be expressed as the same sum, but this time the rectangles from the left with an area of 1 is separated so that the sum is less than 1 plus the integral from 1 to infinity of dx over x to the p. This leaves us with the compound inequality, the integral from 1 to infinity of dx over x to the p is less than the sum from k equals 1 to infinity of 1 over k to the p is less than 1 plus the integral from 1 to infinity of dx over x to the p. From our compound inequality, we solve the integral, which is equal to the limit, as b approaches infinity, of the integral from 1 to b of dx over x to the p. For simplicity's sake, we can express this integral as x to the negative p dx so that we can use the power rule. When we take the integral, we get the limit as b approaches infinity of x to the negative p plus 1 over negative p plus 1 evaluated from 1 to b. This gives us the limit as b approaches infinity of b to the 1 minus p over 1 minus p minus 1 over 1 minus p. Since there is a common denominator, we can combine the numerators to get the limit as b approaches infinity of b to the 1 minus p minus 1 over 1 minus p. Since the convergence p-series only applies to p greater than 1, then b to the 1 minus p will always result in a negative exponent. So the limit as b approaches infinity of this term will be 0, or 0 minus 1 over 1 minus p, which is equal to 1 over p minus 1. We can now apply the integral solution to the compound inequality. When p is greater than 1, 1 over p minus 1 is less than the sum from k equals 1 to infinity of 1 over k to the p is less than 1 plus 1 over p minus 1. As an example, determine if the following p-series converges or diverges. If it converges, find the bounds of the sum. The sum from k equals 1 to infinity of 1 over k squared. This is a p-series where p equals 2, which is greater than 1, therefore the sequence converges. In this case, we substitute p in the bounds equation with 2, then simplify to arrive at the sum being bounded by 1 and 2. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you and good luck with your studies.